presentation? So there's another one after it, right? Or we have, I think we're like a minute away. No, I bet you're right.
Hello, everyone. Hi, good afternoon. My name is Ann Struth. I'm the manager of public programs here at the museum, and I am thrilled to welcome you all here today to our Space and Science Festival, which is an annual celebration of STEM innovation here at the museum. Before we get started, I'd like to share a little bit about who we are. The Intrepid Museum is a private nonprofit foundation. All resources raised are devoted to fulfilling our mission of honoring our heroes, educating the public, and inspiring our youth by connecting them to history through hands-on exploration while bridging to the future by inspiring innovation. Throughout the year, we have compelling programs and experiences for all ages, including family astronomy nights, pop planetariums, and astro cafes, where you can hear about cutting-edge science developments, as well as other types of innovations. We hope to see you back here in the near future. Now, on to today's presentation. The James Webb Space Telescope will be a large infrared telescope launched by NASA and the Space Telescope Science Institute in 2021. Webb will be the premier observatory of the next decade, serving thousands of astronomers worldwide. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang to the formation of our solar system capable of supporting life on planets like Earth, to the evolution of our own solar system. Here to tell you all about this next generation telescope and the discoveries it could make possible, please welcome Dr. Alex Lockwood, Science Communication Lead for the James Webb, and Mike T. Menzel, NASA Mission Systems Engineer for the Webb Telescope.
Okay, can you hear me? Yeah, okay, I'll show. No big deal. So we're just going to trade off here and talk to you, and then we'll have a Q&A. I'm Alex, and so let's start talking about astronomy. It's my favorite subject of all time. How do we explore space? I hope you guys have learned something about space so far since you've been here. Oh, somebody has an answer in the back. That's awesome. That's really great. How do we explore space? Yeah? Do you have an answer? Rockets. Rockets are a great thing. Do you have another answer? You could send rovers, we do that. Oh, okay, one more answer.
We look at space with telescopes like the James Webb or Hubble Space Telescope.
Absolutely. You guys, all three are correct. See me afterwards and you get a pin. So we can explore space in a lot of different ways. It looks like this. This is a beautiful picture from the Gaia Space Telescope that just took this a couple months ago. There are billions of galaxies in here. Look hard, you won't see them all, don't worry. I don't know, some people think that maybe we're going to go out there, and for your Trekkies or your Star Wars fans, we've got both, we don't judge. But really we use telescopes is the #1 way that we look out there. Sometimes we look from the ground and sometimes we look from space, and I'm going to show you something that personally to me is one of the coolest things I've ever seen in my life. This is Galileo. We've been looking into space for over 400 years. 2009 was the International Year of Astronomy because it was the 400th anniversary of the invention of the telescope by Galileo Galilei. And this right here are the actual notes that Galileo took. He was writing a letter to somebody, and in the margins he started taking notes about what he was seeing through his new telescope. And right here on the bottom, these 4 little stars that he saw next to Jupiter, they're not stars, they're moons. And he actually tracked them moving on different days, the 10th, the 11th. He tracked them moving around Jupiter. And this was one of the conclusive pieces of evidence that showed us that not everything goes around the Earth. We actually go around the sun, other things go around Jupiter, and now we know we all go around a giant supermassive black hole at the center of our Milky Way. So, in case you didn't know that, now you do. But this to me is one of the coolest things. We actually still have this piece of paper that he wrote on. And so for 400 years we've been making these discoveries, and we're going to tell you about the thing that's going to make the next set of discoveries.
Okay. Hi, I'm Mike Menzel, and I'm the Mission Systems Engineer for James Webb. I'm going to start off by saying how NASA picked up the ball and carried on from what Galileo started. NASA has put up about 300 telescopes in orbit as of today, but of them 4 were nicknamed the Great Observatories. And the most famous of them, the Hubble Space Telescope, was launched in 1990. Then in 1991, we launched another telescope called the Compton Gamma Ray Observatory. 1999, we launched a telescope, an X-ray telescope called Chandra. And finally, in 2003, we launched an infrared telescope called the Spitzer. Now, of these 4 telescopes, the most famous is the Hubble Space Telescope. Launched in 1990, it's been up there for almost 30 years. Normally, telescopes and satellites don't last that long, but we've had 5 groups of astronauts go up and fixed it periodically. Hubble is still up there, and it's working great, and hopefully it will work long into our mission for James Webb. Hopefully we'll have 2 great telescopes up there. Hubble looks at the universe in ultraviolet light and in the same type of light you and I see, and called visible light. What has Hubble done? Not arguably, I will say that Hubble is probably the most productive science instrument ever done by NASA. It has more scientific, it holds the record for refereed scientific papers. But aside from what it's done from the scientists, it's given us images and pictures that are iconic. They're all actually pop icons these days. It took a picture of a great cloud in space, M16, called the Eagle Nebula, that was nicknamed the Pillars of Creation. This giant gas cloud are places where stars are being born inside those dust lanes that you see, inside those dust cocoons. In another nebula, another cloud of space called the Orion Nebula, it's taken pictures of these pancake little things they call astronomers call them propylids. They're believed to be solar systems being formed. Hubble has also taken what could be the first picture, the first image of an exoplanet. This is an image of a star not far from us called Fomalhaut. And that Fomalhaut has a debris disk around it, a debris of rocks and junk and stuff like that. But there's one little speck that astronomers have been following over the years, and it's believed that little speck, which is moving much like a planet, may be the first image, the first real image of another planet around another star. In 1994, Hubble took a picture of comet Schumacher-Levy. It broke up into 21 different pieces, and each of those pieces slammed into the planet Jupiter. And when each piece did so, a fireball, roughly the size of the Earth, was seen rising up over the planet. That's believed 65 million years ago, a similar event might have been what killed the dinosaurs here on the Earth. So this kind of stuff happens very infrequently, but Hubble actually witnessed it and recorded it. As Alex spoke about earlier, Hubble also provided evidence that in the center of most galaxies there are black holes. Regions where the gravity is so strong, not even light can escape it. How do we know they're there? Astronomers look at things that orbit it, and they're spinning around these things so fast that only the gravity of a black hole could hold it in place. And finally, Hubble has taken an image of something that is so far away, a little galaxy, a little smudge of light that is so far away, its light has been traveling to us for over 13 billion years. And astronomers believe that the universe itself is probably 13.8 billion years old. So as of right now, that is the oldest thing we've ever seen, and we're hoping to see much older. So this is what Hubble has done for us, and for people out in the community, I'm nicknamed the Hubble Hugger, because I love Hubble. Okay, but now I'm also the mission system engineer for the telescope that's going to succeed Hubble. We say succeed because we're not replacing. I'm going to show you in a couple minutes. It's going to be a lot different from Hubble. So when we build a new telescope, I'm an engineer. What I do is I go to the astronomers and I say, hey, what do you want to see? What is it you want to study? The astronomers tell me and my team that, and we convert their desires into a language engineers call requirements, which is kind of stuffy, but I'm going to try to break it down for you in simple terms. If you're going to make a telescope, there's some basic questions that you want to know. The first thing you want to know is, hey, what is it you want to see? And astronomers basically wanted to see about 4 different things, 4 different topics. First, they wanted to see the very first stars that turned on in the universe. And by definition, those would be almost the dimmest things there are to see. And those stars would have turned on over 13 billion years ago. So they'd be very faint. Then astronomers want to see how galaxies evolve over cosmic time, how early galaxies turn into the things that we know of today, like the Milky Way. They want to see how stars are born in our own Milky Way galaxy. And finally, they want to see how solar systems are formed. These were the 4 things they told us about 20 years ago when I started doing this. And in the meantime, in that 20 years, there's a new topic that's come into being. As of today, there's almost 4,000 exoplanets, planets around other stars that we found. And it's believed that the James Webb Telescope should be able to study them in some detail, perhaps enough detail to find biomarkers, evidence of things that might have been produced or might have sustained life. Oxygen, water, carbon dioxide, that kind of things. So this is what astronomers want. Now I turn that into requirements. What's the first one? Well, how big do I have to make the telescope? If I want to see the faintest stars in the universe, that means the telescope has to be very big. Picture light from a star as rain coming down, as a rain of light particles called photons. Your own eye, which is actually pretty small, only collects a little of that rain, so that's why these stars appear faint. If you want to make the faint things appear brighter, make the bucket bigger, make the telescope wider. You'll collect more rain, more light. Well, to see the stars that these astronomers want, which are of the order of a nanojansky. If you want to know what a nanojansky is, it's 10 to the minus 26 watts per meter squared per hertz. Clear as mud, right? Okay, well, I got another way of describing it to you. Take a child's night light, it's about 5 watts. You're all familiar with that. You plug it into the socket. Put it on the moon and look at it from the Earth. That would appear to be 20 nanojanskys. That's the kind of thing we're looking at. So how do we do that? Well, James Webb is going to have to be almost 18 feet in diameter, 6 meters in diameter to collect enough light to see such an object. Okay, a 6-meter telescope. Well, that's doable because today, well, first when I was a young man, the biggest telescope on Earth was that, Mount Palomar, and it was 5 meters in diameter. Today, out in Hawaii, we have a telescope that's 10 meters in diameter, so the engineers know how to do it. One of the things that I also want to point out to you is back in the old days, when they made a big telescope like Mount Palomar, they made one big mirror out of one big piece of glass. It took years to make that piece of glass. When they went to make a telescope like Keck, that's 10 meters in diameter, they realized instead of making one big piece of glass, maybe we'll make that big mirror out of individually small mirrors, shaped and positioned so that they all act like the one bigger one. And that's why you see Keck is made up of 36 hexagons, all shaped and positioned to act like one big 10-meter mirror. So if it's good enough for Keck, it's good enough for James Webb. I can make a 6-meter telescope that way, and instead of using 36 hexagons, I'm only going to need 18. And although we'll be smaller than Keck, the Keck telescope sees its light through an ocean of air, and that air ends up stealing about half the light. So when you really normalize things, when you put things on equal footing, James Webb will actually collect more photons than the Keck. Okay, so we're going to make a big telescope, 6 meters in diameter. We're going to make it out of 18 individual hexagonal mirrors. What color should we look at next? If the astronomers want to see the first things that were born in the universe, astronomers like Alex will tell me they're probably very blue, very hot. That blue light, which has a relatively short wavelength, travels through a universe that's been expanding for 13 billion years. That light gets stretched out. By the time it makes it to us, it doesn't look blue. It doesn't even look red. It looks infrared. So the telescope will have to look in the infrared. Next, and for those of you that are interested, you can visit us at the booth and we can show you this. If you want to see stars that are born in these gas cocoons, light doesn't go through dust and gas very easily, but infrared light goes right through it. It's almost like an X-ray. You want to see stars being born? Look in the infrared. You want to see something in the early universe? Look in the infrared. That's what we're going to build James Webb to do. It'll be an infrared telescope. As an engineer, I can tell you infrared telescopes are a bit of a pain. And once again, you go to the booth and I'll show you why. An infrared telescope will glow brighter than the stars it's looking at if you leave it at room temperature. We have an infrared camera set up there and you'll see for yourself. I could turn out all the lights in the Intrepid and you'd be glowing in the dark because you're room temperature. So if you want to make something, an infrared telescope, you better make it cold. How cold? Well, the mirrors have to be about 50 degrees above absolute zero. Now that mirror, that telescope is going to be 3 metric tons. It's going to be almost the size of a 3-story building. How are you going to do that? I'm not going to build a refrigerator that big. I'm going to build an umbrella, a sun shield. That sun shield will block out the sunlight, all 200,000 watts of it. And if I build it correctly, it'll only let about 0.02 watts through. If that sun shield works the way it's supposed to, that telescope will cool down at 50 degrees Kelvin. And by the way, if that sun shield were suntan lotion, it would have an SPF of 10 million. Okay, but that's not the only thing we got to do to make it cold. we got to get it away from the Earth. The Earth, right now, the Earth is about 300 degrees Kelvin. So, the Hubble Space Telescope orbits the Earth at about 600 kilometers up there. We're not going to be there. We're going to get away from the Earth, 1,000,000 miles away from the Earth, and instead we're going to follow the Earth around the Sun at a point called the second Lagrange point. Now, by putting it there, one umbrella is going to block out the light from the Sun, the Earth, and the Moon, getting us nice and cold. That's the great thing. The bad thing, astronauts have never been out there. So unlike Hubble, that's been fixed 5 times, we got to get this guy right the first time. Okay, so that's how this telescope came to be the way it is. Here's a picture of the telescope with me next to it. It stands about 3 stories tall. It has a sun-shielded umbrella about the size of a tennis court. There's the telescope with the 18 segments. There's the sun shield consisting of 5 individual layers, because, an SPF of 10 million doesn't come just every day. That's what it looks like from the side. Now here's the next big problem with James Webb. That's how big the observatory is. Oh, by the way, there's where the cameras are. There's the ordinary part, the spacecraft, the thing with the thrusters, the computers, the communication system, the easy stuff. And that's what it looks like. We built a full-scale model of it, and there it is there. And Mrs. Menzel's baby boy is somewhere right in the center there, about 15 years ago, and my beard wasn't quite looking like Santa Claus. Here's the next problem. That telescope is pretty big, but it's got to fit in a rocket that looks like that. So how do we do it? Well, we're going to have to fold it up and stow it like that. When I started this business 38 years ago, the first thing an engineer told me was never deploy things on orbit, because it's hard. So this is my last mission. What do? I just totally and absolutely disobey him. So what we got is a video. Folding it is easy. Unfolding it in space remotely, that's the tricky part. We have a video here of how it's going to unfold on orbit, if you could. Right now, the rocket, the Ariane 5 rocket, has launched us out. The first thing that comes out is a solar array for electricity. Now we tilt it a little to make all the mechanisms toasty warm. We do a little thruster fire there. And about the time we pass the moon, the fun starts. Now the deployments start. 2 big panels, one on the front, one on the back, fold down. That sun shield, that umbrella is in there. We lift the telescope up about 1 meter. And in another second, we're going to unfold, almost like the sails on a ship, those very delicate sun shield membranes. Those are covers unfolding. 2 booms are going to come out and pull the 5 layers out. This is all taking place over a 14-day period, roughly a 14-day period. Nice and slowly and carefully, a pulley system will make them taut to get them the right shape. Shortly after that, we'll start to unfold the telescope. The secondary mirror comes down. 2 panels will come out in a second. And there you have it. At the end of 14 days, the largest telescope in orbit. Clap after we do it, please. And by the way, it's at 14 days that I told my family I'm going to disappear for a little while, do a bender that's probably epic. But then I will come back to work and finish it up. Okay, that's it. If you could go to the next slide, please. Well, the telescope's made. Here's the telescope here. It's been we put it together at Goddard. We've tested it down at the Houston Space Center, and it's working great. Next slide. This is a picture of our project scientist, Dr. John Mather, who won the Nobel Prize because he's seen the farthest thing there is to see so far. John actually won a Nobel Prize because he saw the fireball from the Big Bang. And if you want a little explanation of that, Alex can explain that to you later. Next chart. This is the test of it that we did in the Johnson chamber at cryogenic temperatures. By the way, if the telescope's going to operate at 50 degrees Kelvin, we have to test it at 50 degrees Kelvin. Getting something the size of a 3-story building and 3 metric tons down to that temperature is not fun. Don't try it at home. Next chart. Here's a picture of the sun shield. You see a little man in the middle. He's got a theodolite there. He's making sure that we got the shape of it right. Next chart. And here's the spacecraft portion of it now. This is the easy part. that we're testing the spacecraft and the sun shield now. At the end of 2019, we're going to put the telescope and the spacecraft together, do the tests, and then ship it down to the launch site in South America, French Guiana, for its launch. Now, just to sum up, at least from an engineering part, telescopes then and now. When I was a young man, that was the biggest telescope on Earth, 5 meters, weighed about 500 metric tons. It's out near San Diego, California. I would have never dreamed at that time that I would have been lucky enough to be on a team that's building a telescope bigger than Mount Palomar, going 4 times farther than the moon into outer space to see the farthest things there are to see in the universe. So now I'm going to hand it over to Alex, who will explain to you the astronomy of this.
All right. Let's give Mike a round of applause. Honored to share the stage. I don't have quite as much experience, but I know a little bit about the science.
You do.
So as Mike mentioned, it's an infrared telescope. And I encourage you all to go visit our booth at the other end of this floor and play around with an infrared camera. You can see things that your eyes could never see before. It's really cool. It's kind of tricky, but it's really fun, and go learn more about the telescope and touch that material, the sun shield. So why infrared? Let's talk a little bit more about infrared. As Mike mentioned, we're keeping the telescope very, very, very cool. 50 degrees above absolute zero. That's like, what is it, negative 220 degrees Fahrenheit. So if you think 20 degrees is cold, think about negative 220, really cold. And we have to do that to see infrared light. Now, you may have heard of the different kinds of light. Have you heard of X-rays? Yes. Have you heard of microwaves? Okay. Some fun facts about different kinds of light. You're actually much more familiar with them than you think. Our light stays visible. Infrared is heat from our body, okay? And you can go see that on the camera down the hall. Now, microwaves. Have you ever looked at the front of a microwave? Have you ever looked at the door has a little screen on it with these tiny little holes, okay? Now, the holes on that microwave, you're heating up the food, you're actually sending microwaves into the water in your food, and it shakes the water in your food, and that shaking is what heats up your food. So you can't heat like dried food, bad idea, don't try it. But the little holes in the front of the microwave, in the front of the door, are actually big enough that they trap microwaves. The microwaves are too big, they can't get through. But they're big enough that infrared waves are small enough to get out. So when you open an oven, you get all of that heat coming out. All the heat's trapped in there. You open the oven, you get whew. When you open a microwave door, there's no heat, because the heat got out, because the waves were small enough to escape those tiny little holes on the front of the door. But the tiny little holes are smaller than the size of the microwaves, so the microwaves just keep bouncing around inside and heat your food. I don't know, when I learned that, I thought it was pretty cool. Same thing with UV. The reason that you need sunscreen to protect your skin from UV is because UV waves, smaller than what we see with our eyes, they're small enough to penetrate your skin and cause damage. Even smaller than that, X-rays go all the way through the skin into the bone, and that's why we use X-rays to study our bones. So the size of a wave depends on where it can get to and what it can see. So we use infrared to see new things in the universe. And that's number one reason. Number two reason that we use infrared wavelengths. Oh, so I have some examples of what that looks like. This is galaxy invisible and an infrared wavelengths. Spitzer used to be the main infrared telescope we had in space. Now the James Webb is going to blow it out of the water. This is a demonstration you could do over the infrared camera. So here, normally we can't see through a plastic bag. Infrared sees through just fine. However, glass, which we see through with our eyes, this guy's wearing glasses, they're actually opaque. You can't see through them in infrared light. So we get pluses and minuses of different kinds of light, and we need all of the information we can get, so we use lots of different kinds of light to study astronomy. This is what Mike was talking about. Here's a cloud of dust. This is a baby star that has a jet coming out of it. We can see that baby star forming. We can understand what's going on in that environment if we use infrared wavelengths. This is that beautiful Pillars of Creation image, iconic image, lots and lots and lots of stars being formed here. Systems we're going to study. How do stars form? How do planets form around stars? How does water get distributed to those planets? These are all questions that we're going to answer with the James Webb Space Telescope. And using infrared wavelengths, we get right into the heart of that dust. What was opaque is now transparent. So the other thing that infrared wavelengths can do that Mike talked about a little bit was that with the expansion of the universe, light itself gets stretched. So you have stars, we can see stars with our eyes. Those stars emit in light we can see, in visible light. However, as the universe expands, so do the waves. So all of a sudden now things that were visible light, red, green, and blue, have now been stretched, and we can only see them in infrared wavelengths. And this is where the oldest images that Hubble have seen of the oldest galaxies, there's a limit at about 400 or 500 million years after the Big Bang, so like 13.2 billion years. We really want to get to like 13.4 billion years. And that doesn't seem like a lot, but really in terms of cosmic time, I mean, there's a huge difference between a 5-month-old and a 2-year-old. Huge difference. And we want to understand what that entire sequence looks like. There's a lot happening. And only with James Webb can we see those first galaxies, the first stars, because the light has been shifted all the way out into these long wavelengths that we don't see with our eyes. Okay, so hopefully that makes a little bit of sense. We also have an activity at the booth where you can understand, we call it cosmological redshift. The light is shifting redder, redder, redder because it's longer, and we have a cool activity that you can check out at the booth. So, this is an example of that. If you draw a wave on a balloon and blow it up, that's like the expansion of the universe. The waves get longer. So, back to the 4 themes that Mike had mentioned briefly. Let's go through them in a little bit more detail. So we talked about seeing the beginning of the universe. The light that was emitted 13.5 billion years ago and now has traveled with the expansion of the universe, gotten longer, and is finally hitting our eyes or our telescopes. And this is going to help us understand something that Mike mentioned that John Mather got the Nobel Prize for, was even before that, the very first light is called the cosmic microwave background. That light is actually, has stretched so long, it's no longer visible, it's not even infrared, it's microwave, hence cosmic microwave background. Microwave is longer than infrared. So we're looking at the stuff between that and the oldest ones we can see with our eyes. So there's a huge part there that's in the infrared. We're going to study those galaxies and understand what happened after the Big Bang. A lot happened, we don't know where we came from, and there's a lot of chemistry that ended up creating who we are today. So we're really studying the origins of where we came from in a very interesting way. This is my favorite image, I think, that Hubble has ever taken. Well, there's a couple of them. There's the deep field, the ultra deep field, the extreme deep field. And close your eyes. Okay? Now, hold out your hand and stick up one finger. Now, open your eyes and look at that finger against the background. There are 3 billion galaxies behind, no, sorry, 3,000 galaxies. Still, that's a lot. There's 3,000 galaxies behind your finger. The size of this image, there's 3,000 galaxies in this image, one finger. That's how small it is. And you can put your finger anywhere, which is why it works from wherever you're seated, and there's 3,000 galaxies there. There are so many galaxies out there, ones we can only see with a very sensitive infrared telescopes. And because there's so many galaxies out there, we hope that we can find the very faintest ones, and that we're kind of going on like a trial and error. We're going to say, oh, let's look over there. Hopefully there's some galaxies. There's probably going to be, because there's 3,000 of them, and those are the ones we've only seen so far. But we're kind of going on like a little Where's Waldo search. It's going to be fun. So it's not only only telescope that can see the first galaxies, it's also going to help us study lots of different types of galaxies. So, have you heard of dark matter? Yes. I love all the kids raise their hands. So dark matter is this thing that we can't touch, we can't see, we can't even detect with anything, but we know it's there because things are going a lot faster than they should be in galaxies. There's actually a female astronomer about 180 years ago named Vera Rubin who discovered dark matter. Don't let anyone tell you otherwise, because it was her. Sometimes I'll get credit. So she discovered dark matter by looking at the stars around a galaxy, and they were moving a lot faster than they should be, just from what she could see. And matter, it attracts each other, and that makes things move. That's why the Earth goes around the sun, because things get pulled around. And so we discovered dark matter, and we know that it's really important in galaxies because there's a lot of it. We don't exactly know what it does. And it turns out the way that it interacts with material in infrared wavelengths there's a different way to study it. So galaxies are not exactly my cup of tea, but I will tell you what is my cup of tea. Protoplanetary disks. I know, that rolls off the tongue so nicely. So Mike mentioned before, the Orion Nebula is something that we studied a lot with Hubble. It's actually the nebula that is in Orion's sword up below his belt, so you can go see it. You can't really see it with your eyes, but you can tell exactly where it is. It's down the sword below Orion's belt. It's the Orion Nebula, and it's one of the most famous star-forming regions. It's very bright, it's very beautiful, and it's always colored pink because there's a lot of hydrogen. So within this region, there are these things called proplids, or protoplanetary disks. Proplids is not really easier to say either, so I don't know why we did that. But protoplanetary disks. Disks, so they're disc-shaped like a plate of protoplanets, pre-planets. So it's what planets are made out of. And this is what I did all of my research on, or most of my research. And so this one you can see from the side, looks like the side of a plate. And this one you see from the top, looks like the top of a plate. And we use all of these different geometries of the plates, the disks, to study what's inside them. And so this is something that's really hard for people to visualize, and so fortunately, we have lots of data from Hubble, and we can turn that data into beautiful visualizations. So now I have a beautiful visualization that'll actually walk you through into a protoplanetary disk, and then the end is an artist's conception. So let's see what that looks like. So now we are flying into the Orion Nebula. This is actually what it would look like. And you can actually go and download this video online. This is actual data from Hubble. We're flying in. There's lots of gas and dust, and all those little bright dots that you see are stars that are just beginning to form. And matter is colliding and creating new starbursts. And you'll see these little pods that are what we call the protoplanetary disks. And then we zoom into one, and here you have a protoplanetary disk. There's jets streaming out of the young star from all the material falling on. And now we go into that, and you see a young nascent star just beginning to really fuse hydrogen and become a full-fledged star. And then you zoom in, and there's all this gas and dust hitting each other. We want to study that gas and dust hitting each other and how the planets form and why is there, we don't know exactly why there's water on Earth yet. I don't know if you've ever thought about this, but where water would normally freeze is actually further out than where the Earth is. So it should have all just floated away, like it floats in our atmosphere. There's water vapor, humidity in our atmosphere. It should have all floated away. But we have water here on Earth. We don't know why. So that's one of the things we're studying, and we're going to study with the James Webb Space Telescope, is looking into these disks and saying, oh, if I wanted to look at the Earth in another system that was forming, how do I get water there? We also use a lot of computers to do that as well. But another thing, and sort of the final area that James Webb is going to explore, is the bodies themselves that have come out of planet formation. So we have our own case study in our backyard. We have 8 planets, a whole what we call asteroid belt and Kuiper belt. The asteroid belt is between Mars and Jupiter, and is all the leftover rocks that were left from planet formation. And the Kuiper belt is like Pluto and all of the other dwarf planets that we've recently discovered, and it sits further out beyond the orbit of Neptune, and it's all of the leftover ice. So there's a belt of ice and a belt of rock, and 8 giant planets, well, 4 giant ones, 4 smaller ones, but they're all pretty big. And we understand what happened in our own solar system. We also have moons like Europa and Ganymede Europa and Enceladus. There's so many moons. It's like, we just discovered new moons around Jupiter. I don't know how that's possible. That have water on them, that we want to study. Well, there's water over there, there's water on Earth, we have life. Is there life over there? But it's really cold. But maybe the water is underneath the surface, and maybe there's stuff living there. So we're thinking of missions right now to send out there. But our own solar system is one example of how a system can evolve. But we have found, as Mike mentioned, thousands of exoplanets, and they are so different than our own system. We have one giant Jupiter, and it sits out about 5 times the distance of the Earth from the sun. And we thought we knew exactly why it was there, until we found something that was 10 times the size of Jupiter, sitting closer in than Mercury. And you're like, how is that possible? And we have thousands of systems now that we've discovered, some systems with 3, 4, 5, 6, 7 planets in them, all different, and we want to understand, why is there this diversity in planets out there? We have a diversity on the Earth, and it's because we've evolved throughout time. Don't let anyone tell you otherwise. We've evolved through time, and you have all of these variations. Well, we see that diversity in planets. And we want to know, how did we get to be here? And is there anything else even close to like us out there? And the answer is probably yes. So, something to think about. The other really cool thing that James Webb is going to do, because James Webb's not going to find the life. So it's not going to find life. We're not quite at that level yet. But James Webb is primed to find very important molecular signatures. So molecules are things, like Mike mentioned, water, methane, which is cow farts. Very important. Ammonia, carbon dioxide, carbon monoxide, all these things that we're pretty familiar with in our own everyday lives. We know water, we know methane, unfortunately. We know carbon dioxide. And they're actually very abundant in the universe. But they make a huge difference when it comes to, is this livable or not? So, if you take Venus or Mars or the Earth, they're very different when it comes to what they look like in the infrared. These are infrared wavelengths we're measuring. And they all have carbon dioxide. So if you saw that, you'd be like, oh, okay, maybe we can live there because the Earth has carbon dioxide. But the Earth also has these important things like ozone that help protect our atmosphere and our humanity, and water and other things. So James Webb is primed to find the important molecules that help tell us, is it like Venus and we're just going to burn up? Or is it like Mars and we're going to freeze our butts off? Or is it like Earth and like happy Goldilocks medium? So I, as an astronomer, and I studied exoplanets and protoplanetary disks, so excited for the science that Webb's going to do. And we encourage you to come to our booth and learn even more. And Mike has some final thoughts.
Let's give Dr. Lockwood a hand now. Just a couple final thoughts for the audience. First, some of you may be the scientists that use James Webb. I know Alex will. I know hopefully some of you will. Some of you may be the engineers that build the telescope after James Webb. And if you are, please come and talk to me and some of my colleagues. We made a couple mistakes we just want to let you know about. I want you to think of the possibilities and what one of you students may be saying to audiences a couple of years from now. Please, good luck, have fun. Please visit us at this website. Alex and I want to thank you for your attention. I guess there's a question and answer period if you have anything you want to ask.
We have a question over here.
I'm curious when you go from the real visual from Hubble to a visual simulation and what that process is?
The visual, so for example, the visualization that I showed you.
Yeah. When does it move from one to the other and why? The data changes or?
So we get a 2D image, but we have people who are specialized both in determining the distances to those objects, but then also looking at the image in much different resolutions and even different wavelengths. And like with different wavelengths, you can see what's in front of or behind something. And so from there, you can actually make a map of what it could look like 3D. It's a lot. It takes a lot of modeling, but a lot of computer time rather than just the image. But you can get that three-dimensional structure to a certain level of detail. It's actual data, but it's not what the telescope sees. The telescope just sees a picture. So it's taking that picture and reading more information of it, reading the depth. Good question.
We have another question over here.
So once the telescope is launched, in place, everything unfolded, instruments tested, how long do you think it'll be before the first usable scientific images are found?
Well, the commissioning is due to end 6 months after launch, right? But I would, somewhere between, I'd say, 4 to 6 months, the scientists are planning what they call their early release observations, and that's where you'll start to see the first images. And scientists are now discussing what that would be. If you want to add to that, Alex. So.
Well, I can't tell you what they are. Very secretive. I actually don't even know. But yeah, so 4 to 6 months after we launch the telescope, it'll finally be, you know, the different instruments get cooled down and ready and tested and calibrated. And about 4 to 6 months after, we'll take some of the first public observations. But then immediately after that, we're actually going to start taking science, and it'll be publicly available. It's part of a program called the Early Release Science Program, and there's about 5 months. The first 5 months of data will actually be immediately made available to the public and to the science community to start playing around with it, so they can do the most that they can with the telescope, because it's brand new. We don't know what its capabilities are. So I would expect the first scientific results, first scientific paper to come out 7 or 8 months after launch, and then it'll roll on it.
Cool, we have another question over here.
So a question that I have, is there any way for self-performance that I could possibly go back on the presentation, just because that would like help me explain my question a lot easier? Like, is there any way to possibly just go back some
Yeah.
slides?
Yeah, where do you want to go?
I'll just tell you what the slides, I can't remember which one. Okay, that's this one right here. So, as we see all the way to the right, it says the Big Bang and then the Dark Ages. Do we happen to know, like, what's in the Dark Ages, or, like, what's there or something? Like,
That's
yeah.
an excellent question. So earlier, Mike mentioned John Mather, Nobel Prize-winning project scientist of the telescope, the observatory. So the Dark Ages is literally no light escaped. So Big Bang, I mean, you can imagine, it's hard to visualize, but you can imagine everything in the universe being in a ball this size, and then, well, as it, that for about 350,000 years, it was so hot and dense that it was what we call a plasma, and everything, there was no atoms, there was no anything, all of the matter was just jumbled up, really hot, moving together. As it expanded, and the universe has been expanding since day one at different rates, but as it expanded, that material, as things expand, they cool, and as it cooled, finally there was enough room, and it was cool enough for atoms to start to form. When those atoms formed, when the proton and the electron got together, made a neutron, and then when you started having the nuclei, and then when the electrons were actually captured, and you formed your first atoms, the release of energy, it was actually the forming of protons and neutrons, the forming of the atoms released a lot of energy. Energy is light. There was the release of light, kind of like that. It kind of happened in a split second. It released all this light. But before that, all of the light was just trapped. There was no, it's what we call optically thick. It's like a foggy room. Light can't go anywhere. So that's what we call the Dark Ages. And then the moment that atoms formed and photons, pieces of light, were allowed to escape, that is the moment that we see in time all around us, because all of that light is spread out, and now that is the cocoon of the entire universe, that is called the cosmic microwave background. So that light is so old, it's been pulled into microwave wavelengths, but it is the first light, the first moment of light from after the Dark Ages, when no light could escape this hot, dense ball. Does that help explain?
Yeah.
We have a question right here.
Thank you. Ooh, sorry, that's so loud. My question is about when you're on Earth and being near Earth and you try to see chemical molecules, you use IR. This space telescope, the Webb, is designed for IR, right? So if you're really far away and trying to see some kind of CO2 group, that IR light that would have let you know information about its existence has come to you, but also stretched. Does it not stretch so far that you can no longer see with IR?
Well, first, the molecules, I think the molecules that, Alex is looking for are molecules that are, on other planets. That light doesn't get stretched. That's in our own galaxy, the space and the wavelengths don't get stretched like that, so that would still be in the infrared. And if you want to add to that.
Yeah, and actually, so if you're looking at something that is 3 billion light years away, so it was emitted approximately 3 billion light years ago, 3 billion years ago. our own Milky Way, and that's exactly what Mike said, is that the things that we're studying to find life are really in our own Milky Way. We don't have the level of precision. When we go to other galaxies, we can really only study like chunks of stars within that galaxy, or even farther, the whole galaxy. The only precision that we have to get into detail, like in the Orion Nebula, these little planetary systems, that's only in our own Milky Way. Our own Milky Way is only 100,000 light years across, so that light is only 100,000 years old, and that stretches very little. So everything's still stretching, but we're only really talking about great distances to change the wavelength. But that's a great question.
We have another question over here.
What would happen if one day the James Webb telescope didn't work and it was very old? If it blew up, what would happen to the other planets?
Okay, let me make sure I understand your question. What would happen if the James Webb telescope got very old and didn't work? And it blew up? Oh, okay, well, let's take it one thing at a time. If James Webb gets up there and it gets very old, you're looking at an old man who'll be very happy. Okay? And then hopefully by that time NASA and astronomers will be even hopefully building or starting to build the next telescope that will replace it. As for James Webb blowing up, that would be a bad day for me, and that would be very unlikely. I don't think James Webb will blow up. But if it blows up, all I can say is that could be a bad day for me. Okay? And I'm not sure what was the other part of your question, honey? Oh, very little. James Webb is just a speck compared to the other planets. Nothing would happen. Okay?
All right, I think we have time for one more question in the back here.
Do you think we'll ever find life on another planet? I mean, talking about people like us.
Find life?
Yeah.
I think it's out there. It's really far away. I mean, it takes 4 years for the signal from our closest star neighbor to get to us. And what we're looking for right now is what we call biosignatures. So they're things like ozone or water that indicate that we relate to life. But the actual sending of a signal from some life form to us, it just takes so long. You're talking about, we've only been sending messages into space for 50 years, and there's only a handful of stars that are within 50 years radius of us. So it's very unlikely.
Part two of my question, I just thought of it. Is there such a thing as a UFO, and can you explain why people think there is?
Oh, I'll answer that. Are there identified flying objects? Absolutely. There's a mess of them. There's a mess of things that have not been identified. Are they extraterrestrial?
Yeah.
I doubt it.
So how do you explain these things?
Well, I mean, I wouldn't try to explain them unless I had more data on it. But there's definitely, people have definitely seen things that they can't identify. That's true. And without getting some scientific data on them, it would be hard to say exactly what they are. So, I'm not the type of person that would ever call, hundreds of thousands of people nuts because they definitely saw something. But what exactly it is, you'd have to actually see it. I would doubt that it would be extraterrestrial, but I don't know. I suppose there's a 1,001 chance or something along those lines. Maybe it is something, but it's hard to really say until you see some data. And I personally have never seen one. And if they're extraterrestrial, I really want to see one.
Okay, let's hear.
Maybe the museum can give us free tickets to go to Area 51 and see what's really going on there.
I don't know much about Area 51. I suspect that if you were there, you might find it to be a completely anticlimactic. There's probably an Area 53 that they're not telling you about. That's the one you got to worry about.
Okay, let's hear one more time for Dr. Watson. We would encourage you to go visit them over at their display in Hangar 3. You can learn a lot more about the James Webb Space Telescope. Thank you.